Okay, what we need to be able to do is to use this equation called the Stefan-Boltzmann law to look at how luminous a star is going to be. It depends on a couple of factors. The surface temperature, it's the temperature to the power of 4, so the luminosity is very sensitive to the surface temperature. So this is the luminosity. Sigma is the factor by which you determine the luminosity. It's the constant of variation, let's say, and A is the surface area of the star. So this is a Stefan-Boltzmann law to do the luminosity, and this is very important. It basically tells you that if you double the temperature, the luminosity is going to be 2 to the power of 4 times brighter. You're familiar with this from Unit 8. You remember this is the black body curve for different bodies. This is the black body curve for a body which is at 3000 Kelvin, 4000 Kelvin, 5000 Kelvin, 6000 Kelvin. Now remember that the Stefan-Boltzmann law is that the temperature, the luminosity, is proportional to the temperature to the 4th power. In other words, this is 3000, this is 6000, the 6000 is going to be 2 to the 4 times as bright. 2, 4, 8, 16 times as bright. It means that the area under this graph, under this one here, is going to be 16 times as much as the area under this one, because this is the intensity, this is the brightness. The second factor is, as the temperature increases, the wavelength of peak emission is going to get shorter and shorter. For example, when we have a 3000 Kelvin body, the maximum wavelength, the wavelength of maximum emission is going to be 1.2 micrometers. When you have a body which is 1000 Kelvin like our Sun, it's going to be 0.5, 0.6 micrometers. So the higher the temperature, the shorter the wavelength. Okay, for the black body radiation, the area under the black body radiation is equal to the total energy emitted per second per unit area of the black body. Okay, so it's this equation but divided by area. Okay. Another factor is the Wien's displacement law, which is this. When you increase the temperature, note what happens to the area under the graph, which we've looked at, the luminosity, which is the Stefan-Boltzmann law. The wavelength of maximum intensity gets smaller, and here we have it. As temperature increases, the wavelength of maximum intensity decreases, so the peak moves further to the left on the graph. So this is also a way, if you know the wavelength of maximum amplitude, the maximum emission, then we know we can work out the temperature of the surface of the star. And here we have it again. This is a low temperature, 3500, and we have this wavelength, which is 5, 7, 800 nanometers. When we have a temperature of 5500, the wavelength is around 500 or 600 nanometers. The Sun has a temperature of 5500 Kelvin. If we know what the wavelength is, we can divide by the 2.9 times 10 to the minus 3 times divided by the wavelength, and that gives us the surface temperature of the star. Here we have different black body curves for different stars. 3000 Kelvin, note that the peak wavelength is around 1000 nanometers. Here it's roughly 500 nanometers. For a star of 10,000 Kelvin, it's 300 nanometers or something like that. So by using these three formula, the Wien's displacement law, black body curve, the Stefan-Boltzmann equation, and the brightness is equal to luminosity divided by pi for d squared, we can find out many factors about the star. If you know lambda max, you can work out the temperature. If you know the temperature and you know the area, you can work out the luminosity. If you know the luminosity and you know the apparent brightness, the way it appears to be to you, you can work out the distance that it is away from you. Here is an example. Two stars in Orion, A and B, have the same apparent brightness as seen from the Earth. B is a blue giant, which is lambda max is equal to 3 times 10 to minus 7. A is a red giant, lambda max is equal to 6 times 10 to minus 7 meters. Which one is the hottest one? Which one has the highest temperature? Since this has got a shorter wavelength, it must have the higher temperature. You also know that the surface area of A, the red giant, is 100 times the surface area of B. We have to find the relative distances from the Earth. This can be done throughout by making comparisons and using ratios and those three formulae that I mentioned. First of all, find the ratio of temperatures, displacement law. Then find the ratio of the luminosities using the Stefan-Boltzmann law. Then we find the ratio of the squares of the distances using the fact that B is equal to L over 4 pi r squared. Let's go through this using the ratio of temperatures. We know that lambda T is a constant for both of the stars. So this is lambda T for the blue star, lambda T for the red star. Let's rearrange. We find that since this is the ratio of the wavelengths, this is also going to be the ratio of the temperatures. The second point, find the ratio of the luminosities using the Stefan-Boltzmann law. This is the equation. So the luminosity of one is equal to the luminosity of the other. We are told that they have the same apparent brightness. We know that one temperature is twice the other. We know that the ratio of the areas is 100. So we can find the ratio of the luminosities. Find the ratio of the luminosities divided by 1 by the other is equal to, this is the luminosity of the red giant, this is the luminosity of the blue star. We know that T is equal to twice the temperature of the red star. We also know that the areas are a ratio of 100 to 1. So we find out, so if you do this working, you'll find out that the ratio of the luminosities is going to be 100 because this is the ratio of the areas divided by 16, which is the ratio of the temperatures to the power of 4. Then the final step is that the brightness is equal to luminosity divided by 4 pi d squared, where d is the distance between the Earth and the star. For the red star we have this value. For the blue star we have the same equation but with different values. We know that the ratio of the luminosities is equal to 100 to 16, so we can divide these two equations now to find the ratio of the luminosities. So the ratio is 100 over 16, and by putting these values and we know that the apparent brightnesses are the same. BO over BB is equal to 1, 4 pi over 4 pi is equal to 1, so we just find a ratio of the squares of the distances, and then we can square root and find the ratio of the distances, which is 10 to 4. Explain how atomic spectra may be used to deduce chemical and physical data for stars. You must understand this idea of the Doppler effect can give this effect of redshift and blueshift. Here's a star which is at rest. This is the absorption spectrum. There's the Fraunhofer lines. If it's moving away from us, the lines are shifted more to the red parts of the spectrum. If it's moving towards us, it's going to be more moving towards the lines are going to be shifted more to the blue part of the spectrum. So here, with the redshift, the wavelengths are slightly longer, like a fire engine moving away. The alternative is that if it's moving towards you, then these lines are going to be more shifted towards the blue part of the spectrum. So notice these double lines here will go towards the blue end, so you know it's moving towards you. And the ratio of the change in wavelength divided by the original wavelength will give you the ratio of the speed divided by the speed of light. Stars can be arranged into categories according to the features on the spectrum. Spectral classification. We look at the lines, we find the absorption lines, we look at their brightnesses at different frequencies, different wavelengths, so we can determine the temperature from the black body curve. And from that temperature we can work out the luminosity, we can work out the distances as well. So we're going to look at these categories of stars. There are some stars which have lots of strong emission absorption lines, some stars that have weaker absorption lines. Here, for example, we have, this is a very prominent absorption line, which is, I think it's a hydrogen absorption line. We have other elements. Each absorption line shows the presence of an element. Now, are used to classify the stars according to these letters. B, A, F, G, K, M. These are going to be the hottest stars, and these are going to be the cooler stars. A lot of this was done by somebody called Annie Jump Cannon around 100 years ago in America. So O, B, A, F, G, K, M are the categories of stars. And so basically by looking at the spectra of the stars, you're able to classify the star according to one of these groups by where the absorption lines are, or the Fraunhofer lines are. So O, B, A, F, G, K, M. O, be a fine girl or guy, kiss me. This is a way of remembering the order of the spectral classification. Here is a summary table, O, B, A, F, G, K, M. These last two we don't need to worry about. You do need to be familiar with this table. You do need to know that an O is a very hot blue star. You need to know that B is a fairly hot, because 30 to 31,000 Kelvin is very hot, blue star. You need to know that the Sun, for example, is a G star. A G2 star is kind of yellowish and it's between 5,300 and 6,000 Kelvin. Our Sun is around 5,800 Kelvin. And so on. So this table, you need to remember this and make your own notes from.